Okay, now for this example, we are going to imagine we have this very large rectangular slab. One side is perfectly insulated, while the other side is exposed to air at a bulk temperature of 20 degrees Celsius. Now the question we are going to ask ourselves is, what is the rate of heat loss through this surface? Well, let's first tell ourselves that we have a uniform cross-sectional area. We are going to denote that using the variable A for area. Over here, we're going to mark this as position x is equal to 0, while over here, we're going to mark this as the position x is equal to L. Now, as you can see, the direction of positive increasing x values goes from left to right. This is going to be important later when we are worried about our consistency in our signage. Now, if we are to say that this plane right here is infinitely thin, we know that there can be no energy accumulation across it. Therefore, we know that the heat being transferred to this plane via conduction must leave through convection. Now let's expand on this Q convection term. Our Q convection term is going to be equal to some heat transfer coefficient H multiplied by the area multiplied by the temperature very far away, which we're going to denote as capital T infinity, minus the temperature at position x is equal to 0 at any time t. Now, if we are to say that at time is equal to 0, both sides of this slab are perfectly insulated and have a uniform initial temperature, we can write that as the temperature at any position at time is equal to 0 is set at some initial uniform temperature, which we'll say is 80 degrees Celsius. We know that as soon as we take away the insulation from one side, there's going to be heat loss. So let's express this using a temperature profile. Over here, we're going to have position x is equal to 0, and over here, we're going to have our position x is equal to L. And over on this side, we're just going to have our range of temperatures. Now, we just said that at time is equal to 0, this rectangular slab has a uniform initial temperature of 80 degrees Celsius. It is not changing at that point. Therefore, our temperature gradient is going to be 0. We're going to have a flat slope at time is equal to 0. Now, going back to what I said before, I said that the heat being transferred through conduction to this plane must leave via convection. Therefore, those two terms must be equal to each other. Well, we said that Q convection is equal to our heat transfer coefficient multiplied by our area multiplied by the temperature very far away minus the temperature at position x is equal to 0 at any time t. This is equal to our conduction, which is Fourier's law. We know that as negative the thermal conductivity multiplied by the area multiplied by the change in temperature with respect to position evaluated at x is equal to 0. Now we want to check our signage here. Here we have a negative, so let's make sure that is correct and consistent. If we say that the temperature on the inside is higher than that of the temperature on the surface, we know that we will have a positive temperature gradient. If we negate this, we will have negative heat flow. Heat is flowing in the negative direction, which is correct and consistent. Now, what can we say at position x is equal to L, where there is perfect insulation? We know that no heat transfer can occur. Therefore, negative our thermal conductivity multiplied by our area multiplied by the change in temperature with respect to position evaluated at x is equal to L must be equal to 0. Well, we know that K and A are both non-zero terms. Therefore, our temperature gradient must be 0, meaning that the slope on this temperature profile is flat, or 0. So I'm going to illustrate that using horizontal flat lines. Over here, we can mark this as a temperature of 20 degrees Celsius. We know that gradually over time, the temperature of this surface and the temperature of the air are going to become more and more alike. Therefore, at time is equal to infinity, they are the same. So we can say that this temperature gradient is 0 at time is equal to infinity. Now, where is the slope of our temperature gradient going to be the highest? Well, it is going to be up here at 80 degrees Celsius, where our temperature, our initial temperature, is the highest. So we're going to have the steepest slope up here, and gradually our slope is going to decrease over time until we hit that time is equal to infinity and our temperature gradient is 0. So sketching this, we will have our steep slope up here looking like this. And gradually over time, we will see that it flattens out. So that is how you sketch the temperature profile for this example. All right, for this example, we are going to say that we have a coffee cup, a glass mug that is at 90 degrees Celsius. So let's sketch this out. We have a glass mug at 90 degrees Celsius. Beyond that, we have an insulating sleeve. And beyond that, we have air at a temperature of 20 degrees Celsius. Now, if we say that each of these planes are infinitely thin, just like the example before, we can say that the heat loss via conduction through the glass is equal to the heat loss via conduction through the insulation, which is equal to heat loss via convection to the air. Now, writing this equation out using a general Q term, we're going to have Q is equal to the heat leaving via conduction through the glass, which is equal to the heat leaving via conduction through the insulation, which is equal to heat leaving via convection to the air. Now let's sketch a temperature profile for this example. Over here we are going to have the temperature, and down here we are going to section this off into our 3 different sections: our glass, our insulation, and our air. We know that our glass is at a temperature of 90 degrees Celsius, while our air is at a temperature of 20 degrees Celsius. Now let's expand this equation into terms that we are familiar with. We're going to have the magnitude of our heat flow equal to the conduction through the glass, which is Fourier's law, so negative the thermal conductivity of the glass multiplied by our area multiplied by the change in temperature with respect to position is equal to the conduction through the insulation, which is going to be the negative thermal conductivity of our insulation multiplied by our area, multiplied by the change in temperature with respect to position, which is equal to our convection term, which can be written as the heat transfer coefficient H multiplied by our area multiplied by the absolute value of the temperature of our surface of the insulation minus the temperature of our air. Now, how do we sketch a temperature profile for this? Well, let's think this through logically. We know that the thermal conductivity of the glass is going to be higher than that of the insulation. And if these two terms are equal and area is the same, we know that the temperature gradient of the glass must be lower than that of the temperature gradient of the insulation. So sketching this out, we're going to have a temperature gradient with a slope that isn't so steep going through the glass. It then steepens going through the insulation and finally tapers off to 20 degrees Celsius. And that is how you sketch the temperature profile for this example. Okay, for this video, I want to take the same problem as before and start putting more values to things and start considering thermal resistances. So we know that over here we had our coffee, followed by our glass mug, followed by an insulating sleeve, and finally air. We know that our coffee, the temperature of our coffee was 90 degrees Celsius, and the temperature of our air was 20 degrees Celsius. We know that we had heat leaving via conduction through the glass, heat leaving via conduction through the insulation, and heat leaving via convection to the air. And if we remember, those terms are Q conduction of our glass is equal to the negative of the thermal conductivity of the glass multiplied by the area multiplied by the change in temperature with respect to X. Likewise, we had our conduction term for insulation equal to the negative thermal conductivity of our insulation multiplied by the area multiplied by the change in temperature with respect to X. Our convection term for air is the heat transfer coefficient of air multiplied by the area multiplied by the temperature at this surface, we'll denote this as surface 2, minus the temperature of our air. We're also going to include a convection term for our coffee. This is going to be equal to the heat transfer coefficient for coffee multiplied by the area multiplied by the temperature of the coffee minus the temperature at this surface, which we will call T surface 1. Now, if we said we are at steady state and there is no energy accumulation across that plane, that the first derivative of temperature with respect to position is constant. Therefore, the second derivative with respect to position is 0. We know that we start off at this initial temperature up here and end at a temperature down here of 20 degrees. So an initial temperature of 90, and then we're ending at 20 degrees Celsius. So like I described before, the temperature profile is going to look something like this. And we know this because we said that the thermal conductivity value of glass is higher than that of insulation, meaning that the temperature gradient for the glass is going to be lower than that of the insulation. We can also say that each of these materials has some thickness, we'll say is L. And to keep it consistent, I'm going to put this as L glass, the thickness of the glass. And this is the thickness of the insulation. So I'm going to put L insulation. Now we can say that if we know the temperature here, then we know the temperature here. If we divide that by the thickness of our glass, that will give us the slope. Same thing over here. If we know this temperature, then we know that temperature. Dividing by the thickness of the insulation gives us this slope. Multiplied by the thermal conductivity gives us our value for Q. So we have 3 unknown values, which means we need 3 equations. So I'm going to start off by labeling this temperature as T1, this temperature as T2, and this temperature as T3. Okay, so like I said before, we are assuming we are at steady state. So we can have this general Q term equal to all of these terms. So first I'm going to write those out, and then we're going to start substituting in values such as T1, T2, T3, and our lengths. So writing this out first, we're going to have Q is equal to the heat loss via conduction of the coffee. So that's going to be our heat transfer coefficient of coffee multiplied by the area, multiplied by the temperature of the coffee, minus the temperature at that surface. This is equal to our conduction term for the glass, which we said is negative the thermal conductivity of the glass, multiplied by the area, multiplied by the change in temperature with respect to X. This is equal to our conduction term for insulation. So negative the thermal conductivity of insulation times the area times the change in temperature with respect to position. And this is equal to our convection term for the air, which is the heat transfer coefficient of air multiplied by the area multiplied by the temperature at that second surface minus the temperature of the air. Now we already talked about how we can now put values to these surfaces. So instead of just calling this surface 1 and this is surface 2, we can now start saying that this is T1 and this is T3. We also said that these slopes right here are going to be equal to the temperature difference over the length. So let's plug in values for those. So we said Q is equal to the heat transfer coefficient for coffee multiplied by the area multiplied by the temperature of the coffee minus the temperature at this surface is now T1. This is equal to the negative thermal conductivity of glass multiplied by the area multiplied by the slope, which is the change in these two temperatures over the thickness. So T1 minus T2 divided by the thickness of the glass, which is equal to the negative thermal conductivity of our insulation times the area times T2 minus T3 over the thickness of the insulation. And this is equal to our convection term for the air. So the heat transfer coefficient for air multiplied by the area multiplied by T3 minus the temperature of the air. We can relate this long equation to something a little bit more simple, which is Q is equal to U multiplied by the area multiplied by the temperature of the coffee minus the temperature of the air. U is our overall heat transfer coefficient. And if we're thinking about this process overall, we're going to have our starting temperature T coffee minus our final temperature T air. Now I want to introduce something that is very different, because we can actually relate this to Ohm's law. The change in voltage is equal to the current times the resistance. Because I want to start talking about thermal resistance through each of these. So we know we have two different equations for conduction. There's a Q conduction equation and there's a Q convection equation. The Q conduction equation is the thermal conductivity multiplied by the area multiplied by the change in temperature with respect to position. In this case, we're going to count our position as L, the thickness. And we know convection is the heat transfer coefficient multiplied by the area multiplied by a change in temperature. We can also write this as thermal conductivity area change in temperature divided by L. So now we can rearrange each of these to kind of be in this format. The way we're going to do so, we're going to plug in this Q is equal to K, A, change in T divided by L. Same over here. Convection is equal to the heat transfer coefficient multiplied by A multiplied by some delta T. Rearranging each of these, we'll find that the change in temperature is equal to Q divided by thermal conductivity multiplied by area. Down here, we're going to get the change in temperature is equal to Q multiplied by 1 over the heat transfer coefficient times A. Looking at this, we can see that our delta T term is like our delta V term. So our change in temperature is like our change in voltage. Our Q term is related to the current, while this thickness over thermal conductivity multiplied by area and 1 over our heat transfer coefficient multiplied by area is analogous to our resistance term. Therefore, we can say that the resistance for something experiencing conduction, heat loss by conduction, is going to be the thickness over the thermal conductivity multiplied by the area. Whereas our convection terms for resistance are going to be 1 over our heat transfer coefficient multiplied by the area. So rewriting this into our terms, we can see that the resistance of the glass is equal to the thickness of the glass divided by the conductivity of the glass multiplied by the area. The same goes for insulation, as they are both experiencing conduction. Thickness of the insulation divided by the thermal conductivity of the insulation times the area. The resistance term for coffee is going to be our resistance convection term, 1 over HA. So 1 over the heat transfer coefficient for coffee times the area. Same for the air. It's going to be 1 over the heat transfer coefficient for air multiplied by the area. Now we can say that our entire process is in series. This is because it's following a sequential type of flow. We know that the total resistance for something in series is simply just adding together each resistance. So we can say that our total for our process is just going to simply be adding all of these terms that we just found. So let's write that out. We can say our R total is equal to the thickness of the glass divided by the thermal conductivity of the glass multiplied by the area plus the thickness of the insulation divided by the thermal conductivity for insulation multiplied by the area plus 1 over the heat transfer coefficient for coffee times the area plus 1 over the heat transfer coefficient for air times the area. Now we can see that we have this singular area term that is not changing. They all have the same area, so we can actually just take that out of our equation. So we're going to have that our total resistance for this is equal to 1 over our area multiplied by thickness of the glass divided by the thermal conductivity of glass plus the thickness of the insulation all over the thermal conductivity of the insulation plus 1 over the heat transfer coefficient for coffee plus 1 over the heat transfer coefficient for air. And that is how you solve for the thermal resistances in our example.